On the morning of the 30th of June 1908, something exploded above a remote stretch of Siberia. The explosion was heard 800 kilometers away. The shockwave traveled around the world, twice. It was recorded by barometric pressure sensors in London, in Washington, in St. Petersburg, in Batavia. In the forests below the explosion, approximately 80 million trees were knocked flat across an area of 2,150 square kilometers. The trees did not burn, they were felled by the pressure wave, pointing outward from the center in a radial pattern like the spokes of an enormous wheel. No crater was found. No meteorite fragments were recovered, not for decades, and even then only in the form of microscopic particles embedded in the soil. The largest impact event in recorded human history left almost no physical trace. The Tunguska event, as it came to be known, has been studied for over a century. The basic question, what exactly caused the explosion, was only confidently answered in the last 20 years. And even now, some aspects of the event remain genuinely unexplained. The explosion occurred at approximately 7:17 in the morning, local time. The epicenter was near the Podkamenaya Tunguska River in what is now Krasnoyarsk Krai, Russia, one of the most remote and sparsely populated regions on Earth. The nearest significant settlement was the trading post of Vanavara, approximately 65 kilometers to the south. At Vanavara, the effects were extreme. Witnesses reported a blinding white-blue light crossing the sky, brighter than the sun, followed by a pillar of fire that seemed to reach up to the horizon. The heat was intense enough that people in the open felt it on their skin. Seconds later, a shockwave arrived and knocked people off their feet. Windows shattered. Doors were torn from their hinges. One eyewitness, a trader named Semenov sitting on his porch at Vanavara, described the heat as so intense he felt his shirt was on fire. He was 65 kilometers from the blast center. At the Lena Goldfields telegraph station, hundreds of kilometers away, the barometric pressure needle swung so violently that it went off the scale. Seismic stations as far away as Jena, Germany recorded the shockwave. The disruption to the Earth's magnetic field was detected in instruments across Europe and Asia. In the days following the explosion, the night skies across Europe, Siberia, and Central Asia were luminously bright, bright enough to read by outdoors in the middle of the night. This continued for several weeks. It is now believed to have been caused by fine debris from the explosion being carried into the upper atmosphere. Despite the scale of what had happened, no scientific expedition reached the Tunguska region for nearly 20 years. The remoteness of the site made access extraordinarily difficult. The Russian Revolution and the years of civil war that followed made systematic scientific work in Siberia essentially impossible. The first serious expedition arrived in 1927, led by a mineralogist named Leonid Kulik, who had been convinced by eyewitness testimony and newspaper accounts that a large meteorite had fallen in the region. What he found was not what he expected. The forest had been devastated across a vast area. The radial pattern of felled trees was exactly what would be expected from a massive pressure event originating at a single point in the sky. At the very center of the pattern, some trees were still standing. They had been stripped of their branches but remained upright, because directly below the explosion, the pressure wave had come straight down rather than at an angle. But there was no crater. Kulik searched for it systematically. He drained a swamp in the center of the impact zone, expecting to find a meteorite below it. He found nothing. He led 2 more expeditions to the site before the Second World War. He never found a crater, and he never found a meteorite. Kulik died in a German prisoner of war camp in 1942, the meteorite still undiscovered. The absence of a crater and the absence of meteorite fragments led to decades of competing theories. Some were serious, some were less so. Among the more unusual proposals, a natural hydrogen bomb caused by an unusual combination of atmospheric conditions. a piece of antimatter which would have annihilated completely on contact with normal matter, a miniature black hole passing through the Earth, a comet made entirely of ice which would have vaporized completely on impact. The antimatter and black hole theories have been rejected on physical grounds. Both would have produced effects that were not observed. The comet theory persisted for longer. A comet made primarily of ice and dust could, in principle, disintegrate almost completely in the atmosphere, leaving little solid material behind. It was a plausible explanation for the absence of a crater and the absence of large fragments. The problem was the lack of physical evidence for a comet, specifically the absence of a visible tail or trail in the weeks before the impact. Comets of sufficient size to cause the Tunguska explosion would have been visible to observers worldwide for days or weeks before entering the atmosphere. No such comet was reported. The current scientific consensus, arrived at through decades of analysis of soil samples, tree ring data, and computational modeling, is that the Tunguska event was caused by a stony asteroid approximately 50 to 80 meters in diameter, which entered the Earth's atmosphere at high speed and disintegrated in a large airburst at an altitude of between 5 and 10 kilometers. An airburst of this type releases its energy in the atmosphere rather than at the ground surface. No crater forms. The object is largely vaporized. What reaches the ground is a pressure wave, a thermal pulse, and microscopic debris. This explanation fits the physical evidence. It explains the radial felling of trees, the absence of a crater, the global detection of the pressure wave, and the presence of microscopic silicate and magnetite particles found in the soil at the site in later expeditions. The scale of the energy release is estimated at between 10 and 15 megatons of TNT equivalent, roughly 1,000 times the energy of the atomic bomb dropped on Hiroshima. In 2013, a smaller but well-documented event provided a point of comparison. On the 15th of February, a meteor entered the atmosphere over the Russian city of Chelyabinsk. It was roughly 20 meters in diameter, a fraction of the estimated Tunguska object. It released approximately 0.5 megatons of energy. It shattered windows in 7,000 buildings across 6 cities. It injured 1,500 people. The shockwave was felt across a wide area. Dashcam footage captured the event from hundreds of angles. The Chelyabinsk meteor released approximately 1/30th of the energy of Tunguska, and yet it caused significant damage to a populated area and injured over 1,000 people. The Tunguska object, 30 times more powerful, detonated over an essentially uninhabited forest. The timing mattered enormously. Had the Earth been rotated 4 hours differently at the time of impact, Tunguska would have detonated above St. Petersburg. What the Tunguska event established was, and what has shaped planetary defense research ever since, is that the Earth is not protected from relatively small objects capable of causing catastrophic damage to populated areas. A 50 to 80 meter asteroid is not a planet killer. It would not cause a mass extinction, but it would destroy a city. The Tunguska event happened 116 years ago in one of the most uninhabited places on Earth. No one was killed. The devastation was total, but the witness was largely forest. The question that planetary scientists have been working on ever since is not whether something like this will happen again. It will. The question is whether we will see it coming. This has been the Pale Dossier. File 09 remains open.